In this video, we're going to review some historical number systems that specifically used a positional system. Now, our number system is a positional number system of base 10, and before we start looking at the historical number systems, let's first review some rules of exponents and how we might work with a positional number system. In our first example, we're asked to find each power, and we've got 10, and the way we know this is an exponent is you see in the upper right corner, you've got a number that's also smaller in scale than the other. So this is 10 raised to the exponent 0, and that's going to be the value 1. And here we've got an important rule. Any number raised to 0 as an exponent is equal to the number 1. So even if we had 256, if it was raised to the 0 power, its overall value is 1. Next, we've got 10 to the first power. That's going to take on the value 10. And if you've got a calculator, the exponent button looks somewhat like this. So you would type into your calculator 10, exponent button 1, and it would give you 10 back as a result. But anytime you raise a number to the exponent 1, that has a special property that any number raised to 1 as an exponent gives you that number back as a result. So if we were raising 1035 to 1 as an exponent, our answer would be 1035. Now, exponents are really just showing repeated multiplication. So if we see 2 cubed, that's the same as 2 times itself 3 times. Sorry, that last one should be a 2. Which you could just say 2 times 2 times 2 in your calculator, that's 2 cubed. Or you could type into your calculator 2, exponent button 3, and in either case we would get the value 8. Now, either by multiplying this out or type it into your calculator, find the next value. Remember, 7 to the 4th power means you're multiplying 7 by itself 4 times. And here I recommend you pause the video, get the answer, unpause to check your work. So we've got 7 times itself 4 times, or 7 exponent 4 in our calculator, and we would get 2,401 in either case. Now, one of the reasons we want to review how exponents work is that is how positional number systems work. It's all based off of exponents of a certain number, in our case, in our number system, base 10. Now, if you hear in our class lectures, or if you're reading the textbook homework problems or quizzes, and you see the phrase HinduArabic, that just represents the name for our number system. So remember, HinduArabic is just a phrase for what we call our number system. Now, positional numbers use a multiplicative grouping system instead of just repeating the same symbols, so you have to just keep adding those symbols over and over to express what you're looking for. And that's efficient because the power associated with each multiplier can be understood based on the location in the number. A quick example of that is if I asked you if there's a difference between these two numbers, you would clearly say yes without even thinking. You would say, yeah, this is 12, this is 21. But how do we know that they're different numbers? Because they actually use the same digits. Both of these numbers have a 1 and a 2. The key difference that tells us one of the numbers is 12 and the other is 21 is the location of the 1 and the location of the 2, right? Since if we're looking at the number 12, since we've got a 1 in the first place to the right, we've got a 2 in the first place to the right, and a 1 in the place to the left of that, we know that this represents the idea that you've got 1 grouping of 10 plus 2 groupings of 1. And that's what gives us the idea of 12. But in the case of 21, since the farthest digit to the right is a 1 and the one to the left of that is a 2, that tells us that you've got 2 groupings of 10 plus a single grouping of the digit 1. This is why our number system is a positional number system with base 10, because based on where the digit is, we know to multiply it by appropriate digit or multiplier of 10. For instance, 234, we know that since there's a 1 and a 4 in the digit farthest to the right, that means we've got 4 times 1 plus, since there's a 3 in the digit to the left of that in the tens place, that means that we've got 3 times 10. And finally, since we've got a 2 in the third digit to the left, ones, tens, hundreds, that means we've got 2 times 100. Now, this is probably something that you're so used to that you don't even think about it. It just comes naturally. And as I explain it, don't let it yourself be confused. This is stuff that you've been doing for years and years and years. Just as a quick recap of the positions in our number system, the first digit farthest to the right before the decimal point, is the ones place. Then as you move to the left, you keep increasing by a multiple of 10. So at first we're in the ones place, then we get to the tens place. As you move to the left, then we're at the hundreds place. Keep moving, now you're at the thousands place. Notice we keep increasing by a multiple of 10 as we move over. Then 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, and it would keep continuing out if we had more and more digits that we were looking to the left of billions, and on and on and on. Now, for a positional system to be successful, one key important idea is that you've got to have a symbol for 0, because that needs to be a placeholder in case you don't have one of the powers of bases needed at that exact moment. For instance, 5,020, we need to be able to represent that there are 5 times the 1,000s plus 2 times the tens, and actually we don't maybe think of it as much, but there's 0 times the 100s as well, plus 0 times the ones. But the idea is, if we didn't have the concept of 0, then how would we distinguish between 52, as in 5 tens and 2 ones, and 5,020, which is 5 1,000s, plus 0 100s, plus 2 tens, plus 0 ones. So it's important to remember, if you're going to have a positional number system, you've got to be able to represent that some bases might not be used in a particular number. Now, before we look at these historical number systems, we're going to quickly review expanded form, which is just a way of clearly writing out exactly what multiples of tens do we need in a number in an expanded form. For instance, we're going to translate what is this in terms of our Hindu-Arabic numbers. How could we simplify and write this out? It might help to know a few exponents related to 10. 10 to the 0 is 1. 10 to the first is 10. 10 to the second is 100. 10 cubed is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. And the pattern would continue. 10 to the sixth would be 1,000,000. You just keep adding a 0 for each increasing exponent of 10 that we're looking at. Now, with this in mind, whenever we look at this expression, we could rewrite this as, this is the first one is 3 times, 10 to the fourth is 10,000. So this is the same as 3 times 10,000 plus 2 times 1,000, because 10 cubed is 1,000, plus 5 times 100, 10 squared is 100, plus 8 times 10, plus 1 times 1. Now we can simplify this. 3 times 10,000 is 30,000. 2 times 1,000 is 2,000. 5 times 100 is 500. 8 times 10 is 80, plus 1. Adding all these together, either just in our mind or with our calculator, we would get 32,581. So this is how we would be more familiar in seeing the number, but notice all we did is represent the number in a slightly different way, telling us exactly how many each multiple of 10 we need. To make 32,581, you need 3 10,000s, plus 2 1,000s, plus 5 100s, plus 8 10s, plus 1 1. Now, in our next example, it's very similar. It's just a different number. This is a great opportunity for you to practice what we just learned. So throughout this course, I'm going to keep in the videos giving opportunities for you to pause. And in this time, you should pause the video, work out the problem on your own, and then unpause and you'll see the solution explained to you. That's when you would just check your work line by line. If you got it right, great. If you didn't, maybe try to, based on the video, see how you could correct your work. And remember, even if I'm not telling you to pause, you could pause the video at any time if you feel like it's helpful to you. So remember to pause when requested, and also know that you can pause at other times as well. So let's pause, work on this problem, unpause when you're ready to check your work. Now this problem comes down to just simplifying what we see written. 10 to the 5th is 100,000, so this is 9 times 100,000, plus 2 times 10 to the 4th is 10,000, plus 0 times 10 cubed, which is 1,000, and 0 times anything is just 0, so this really doesn't contribute anything, but it might help us just keep track of where we are to write it out. Plus 4 times 10 squared is 100, plus 0 times 10 to the 1st is just 10, but again 0 times anything is 0, so that doesn't add anything, plus 3 times 10 to the 0 is another way of writing 1, so we would get 900,000 plus 20,000 plus 400 plus 3, adding all that together, and we would get 920,403. So notice we went from an expanded form of a number to the condensed form. In the next example, we're just going to go in the reverse. We're going to go from a number written in our number system, and then we are going to break it down into its component pieces. And the best way to do that is to just say the word out loud, say the number out loud, and just by reading it out loud, you're going to tell yourself exactly how many of each type you need. For instance, as I read this, I'm going to say 756. Just saying that out loud tells me that I need 7 times 100 plus 5 times 10 to get the 50 plus 6 times 1 to get the 6. Now the final step is to rewrite this in terms of exponents. The reason behind this is how you express a number in a certain base. You know, it's not just 1, 10, and 100. 1 is 10 to the 0. Ten is 10 to the 1st, and then 100 is 10 squared. So this could be simplified to be 7 is just 7 times 10 squared, because 100 is 10 squared, plus 5 times 10 to the 1st, plus 6 times 10 to the 0. And then we can see exactly what multiple of 10 we need to multiply each position by to get our final answer. So that'd be our answer there. Now, in the next example, we are going to rewrite this number in expanded form, and in case you can't see the number clearly, it is this. This would be a great opportunity for you to pause the video, attempt the problem on your own, unpause when you're ready to check your work. So I would recommend starting this again just by saying the number out loud, 4,568. That tells me I need 4 thousands plus 5 100s plus 6 10s plus 8 1s. The final step is to just rewrite these as exponents on 10 based on our chart. So we've got 4 times 10 cubed plus 5 times 10 squared plus 6 times 10 to the 10 to the first because it's 10, plus 8 times 10 to the 0 power. And that would be our answer. Now our last example of this kind is this. Again, you might want to pause the video now, work out the problem on your own, and then unpause. So here we've got the number 46,478. Now in order to get to 46,000, we first need to have 4 times 10,000. That gets us our 40,000. And then what remains is we've got the 6,000, which comes from 6 times 1,000. Plus the 400 comes from 4 times 100. Plus the 70 comes from 7 times 10. And then the 8 comes from 8 times 1. Rewriting that as powers of 10 based on our exponents of 10 that we've got off to the side, we know this could be 4 times 10,000 is 10 to the 4th. Plus, 6 times 1,000, 1,000 is 10 cubed. 100 is 10 squared. Multiply that by 4. 10 is just 10 to the first. And 1 is 10 to the 0th power. And that would be this number written out in expanded form. Now we get to our first historical number that used a positional system, and that is the Babylonian system that we're going to learn about today. Now, Babylonians used a base 60 in their system. We're going to explain what that means in a second. And some special features of the Babylonian system is that first, as mentioned before, they used a base 60 system. So they used a base 60. And their numbers are written with the smallest base grouping to the right, similar to us. And as the groupings continue to the left, the multiplier of the base gets larger and larger, first at base 1, then 60, then 3,600. And where does 3,600 come from? That's just 60 squared. So what's going on is 1 is 60 to the 0th power, 60 is 60 to the first power, 3,600 is just 60 squared. So notice as the groupings move to the left, they increase in a multiple of 60. So we're not going to see it in our class, but the next one would be 60 cubed, which would be even a larger number that you could find in your calculator. Now, the Babylonian system lacked a 0 in the earliest system, and because of this, it was difficult to express when missing powers of the base were there, and just general spacing, so that is one drawback of the Babylonian system. Now, in terms of how it's expressed, it's pretty simple in terms of symbols. There was 2 symbols. The 1 is just like this V, the 10 is this sideways V, and then based on how these symbols were grouped together and this implied multiplier, you could figure out what the number was. So let's start working a problem, because I think this is best understood seeing a problem worked out, and then you'll kind of catch a hold to the different meanings behind their system. Now, as we look at our first example, we're going to remember what these symbols represent. Okay, and specifically, we're looking at example A here. Now, how do you differentiate between what's written in A and B? Let's just talk about the differences first, and then we'll start actually simplifying these Babylonian symbols. The first thing I want to draw your attention to in A is there is just a single grouping. Notice that if you look at the farthest right of the number, do you see that we've got the 1s written and then the groups of 10s written all in one thing? Whereas B, I think we can see just two distinct groupings of symbols. The first ones, do we see that there's a space in between? So we know that it's the first group and then the second group. And other than this space, there's another way that you can tell that these are two different groups. Do you see that here you've got the ones and then it's followed as you go to the left by the tens? But then it becomes the ones again? That's kind of out of order, right? Because of that, we know in addition to this space in between, that this is to be seen as one group and this is to be seen as a different group. Okay, now let's actually explain how you would go about translating these to our number system once we've got a hold of how they express the different groupings of numbers. When there is only one group, then we only have the base 1 multiplier. So what you do is you just translate what these symbols are and multiply it by 1, and that's your number. So for instance, I've got 10, 20, 30, 40, 41, 42, 43. But since there's only one group, I just multiply that by 1. So this represents, in our number system, the number 43. And any number under 60 in the Babylonian system will be grouped together just by a single group. It's only when you go above 60 that you have to have multiple groupings to represent that number. Now for the next problem, since there's two groups, what I've got to do is I've got to translate what each symbol grouping means separately and then multiply it by the appropriate multiplier based on which group it's in. So for instance, the first base is multiplied by base 1, but the second base is multiplied by base 60 because as we go to the left, it gets multiplied by a higher power of 60. So this is 10, 20, 21, 22, 23, and since it's in the first position, that means we're taking 23 multiplied by 1, and we're going to add that to the next grouping. 10, 20, 30, 40, 50, 51, 52, 53, 54, 55, 56. But since it's in the second grouping, it's implied that you multiply that number represented by 60. So again, why are we multiplying this one by 1 and this one by 60? Because this is the first group to the right, so it gets multiplied by 1 in their system. This is the second group. This is the group immediately to the group at the right's left. There's probably a better way to say that, but you'll see what I mean. So it gets multiplied by 60. Now we're going to have to calculate this in our calculator. 56 times 60. That's 3,360. 23 times 1 is just 23, so we're taking this 3,360, adding it to 23, and our final answer is 3,383. So this grouping, these two groupings of symbols in this order, in the Babylonian symbols, represents our number, 3,383. Now in part C, you've got an opportunity to practice this on your own, but let's just talk through it a little bit. Take a moment to think about how many groupings you see in this problem. Do we agree this is our first grouping, which we know represents getting multiplied by 1. This is our second grouping that we know means get multiplied by 60. This is our third grouping, which means be multiplied by 3,600. Once we understand the position and what it means we multiply by, we just need to translate each group of symbols and multiply them correctly. I'd recommend at this point you pause the video, work out this problem completely. When you're ready, unpause and check your work. So here we've got 10, 20, 30, 31, 32, 33, 34. Since it's in the first place to the right, we multiply it by 1. And as we go to the left, it just gets multiplied by a higher power of 60. So here we've got 10, 20, 21, based on how these symbols should be read. So we've got 21, but since it's in the second position, it gets multiplied by 60. That we're adding to 10, 20, 21, 22, 23, 24, 25, but since it's in the third position, it gets multiplied by 3,600. We'll definitely want our calculator out for this. So for the 34 times 1, we know that's 34. 21 times 60 is 1,260. 25 times 360, 3,600. 90,000. Adding all these together, and we get the number 91,294. So our number can be represented in the Babylonian system like this. And for the Babylonian and Mayan numerals, particularly those two, all you need to be able to do is to go from their system to ours, not the reverse direction. So notice we just went from their number system and we translated it to our number system. That's the only way we need to go for the Babylonian and Mayan. Now we're almost done with this video. We're just going to introduce the Mayan system, and it's very similar to the Babylonian with a few key details that are different. So you've already kind of gotten used to the idea of this positional number system. Now let's just focus on the few details that differentiate it from the Babylonian system. Mayans use a base 20 system with only one difference. It's actually a modified base 20. And another thing is they write their numbers vertically. So the lowest base would be at the bottom, and then as you increase, the base value increases. So specifically, the first grouping is base 1, which is just 20 to the 0th power. The second grouping, as you increase vertically, is base 20, which is just 20 to the 1st power in terms of exponents. Now the reason we say it's a modified base 20 is the third place we would expect to be 20 squared, which is actually 400. But the Mayans used a modified base 20. Instead, they just used base 360. And some historians and people who study the Mayans speculate that is because of their understanding that there are 365 days in a year. 360 is a close approximate of that. But that's why we call it a modified base 20. Next is the base 7,200, which is just the previous base 360 times 20. Now, we don't have to remember all of this. This was just to try to explain the modified base 20. All you need to know is that with the Mayan numerals, they start from the bottom and go up. The first grouping gets multiplied by 1. The second grouping gets multiplied by 20. The third grouping gets multiplied by 360 if there is one. The fourth grouping, if there is one, gets multiplied by 7,200. And what symbols do the Mayans use? Well, first of all, the Mayans had a symbol for 0, so that's nice. We can represent, if we're omitting a base, just kind of think of this as your empty canoe. I don't know if that's what it really is, but it reminds me of that. And then for 1, we've got the dot. For 5, we've got the line. So let's start working on some examples of Mayan numerals. Okay. Now here we've got 2 examples. We're going to go through the first one together, and then I'm going to give you time to take the second one on your own and pause the video. With the Mayan numerals, we know that we focus on the groupings vertically, and the way you can tell if there's a grouping is first, do you see that there's a space between these groups, and additionally, we go from line, line, dot to line again. That tells you it's a new grouping. And if these 2 dots were supposed to be a part of these groupings, they would be written a lot closer. So we can be pretty confident to say that we've got the first grouping, the second grouping, and the third grouping. all we've got to do is translate these symbols separately and then multiply them by the implied base based on their location in the vertical stack. So this first symbol grouping represents the line is 5, the second line is 10, the dot is 11. It's 11 times 1 because it's in the first position that we're adding to. One line is 5, based on this, 6, 7, 8, 9. But since it's in the second position, it's implied that you multiply those 9 by 20. And then you add it to, notice the next grouping is just 2 dots, 1, 2, based on this symbol. But since it's in the third position, you multiply it by 360, so 2 times 360. And remember, we're getting the multipliers because of where the grouping is in the numeral. Okay? And where are we getting the 1, 11, 9, and 2? It's because of what are these symbols when you translate them based on the Mayan symbols here. Okay? Now, with our calculator, we can find these answers. 2 times 360 is 720. That we then add 9 times 20, 180. That we add to 11 times 1 is 11. Add these three together, we'll get our final answer. So we've got 720 plus 180 plus 11, and our answer is 911. So these Mayan symbols represent our number of 911 when translated. Now I'm going to zoom in on the next problem so that you can see it a bit better. Now on part B, I'd recommend that you take a moment and pause the video, translate the problem on your own, and then unpause to check your work and the solution will be discussed. So pause now. This is our last example of this section of the notes. As we look at this problem, we can see that there's actually 1, 2, 3, and even a fourth grouping for this problem. Our first group, the 0, our second group separated by our last group. So we are going to know that for the first group, it gets multiplied by 1 because it's at the lowest vertically, and this is how the Mayan system works. Translating this group of symbols, 5, 10, 15, 16, 17, 18, 19, multiplied by 1 that we're adding to. This is a symbol for 0, but since it's in the second position, it gets multiplied by 20. But 0 times 20 is 0, so you don't have to write this, but if you want to, it can help you make sure it's all complete. Plus, we've got the symbols for 5 and then a 1, which is 6, times it's in the third grouping, so it gets multiplied by 360. Plus, we've got just a single dot, that's a 1. But since it's in the fourth grouping vertically, it gets multiplied by 7,200. So if we find what each of these items are separately and add them together, we will get our final answer. So 1 times 7,200 is 7,200. Let's get our calculator for the remaining ones. So we've got 6 times 360. That is 2,160. Plus 0 times 20 is just 0, but you could check that also in your calculator. 0 times anything is 0, which we should differentiate from 20 to the exponent 0 is different than 20 times 0, right? 20 times 0 is 0. Anything to the exponent 0 is 1. So do keep in mind those are different operations. And then anything times 1 is just itself, so 19 times 1 is 19. But you could also verify that with your calculator if you like. Adding all these together, and we're going to get our answer. 7,200 plus 2,160 plus 0 plus 19 is 9,379. So our answer is 9,379. Now notice when we turn the page, our last page of these notes list our homework, and that's always going to be the case. So if you want to find the homework for a certain section, you would go in our note packet, go to the end of that section, so after we've introduced all the material, and then you see the textbook problems listed out. All of them are odd, so you are encouraged after you complete a problem to check your answer in the back of the book. If it's correct, go on to the next problem. If it's incorrect, try to see how you could correct it, and if you're unsure, remember you can seek help via our office hours that are posted about in Canvas. You could send me a message through Canvas or our school email, and you can go to the school's math lab as well.